Have you ever wondered what gives some rare earth magnets their incredible strength, or why your smartphone screen glows so vividly? Behind these everyday marvels lies a family of elements called the lanthanoids, mysterious metals tucked away in the F block of the periodic table. Let's dive in. The lanthanoids comprise 14 elements, beginning right after lanthanum, from cerium, atomic number 58, to lutetium, atomic number 71. What makes them special is the progressive filling of the Fourier F orbitals, which gives them unique magnetic and optical properties. Though they're placed below the main body of the periodic table, make no mistake, they belong to the sixth period and contribute extensively to modern technology. While the term rare earth elements might make them sound scarce, many lanthanoids like cerium are more abundant in Earth's crust than lead. These elements might be quietly sitting in row 6, but their role in lasers, phosphors, batteries, and alloys makes them superstars in the real world. Across the lanthanoid series, both atomic and ionic radii show a steady decrease as the atomic number increases. This gradual and consistent reduction in size is known as the lanthanoid contraction. It occurs because the electrons being added occupy the Fourier F orbital, which has very poor shielding ability. The ineffective shielding means that the increasing positive charge of the nucleus is not fully offset, so the effective nuclear charge on the outer electrons increases. As a result, the outer electrons are pulled closer to the nucleus, leading to smaller atomic and ionic sizes. One important consequence of the lanthanoid contraction is that it causes elements in the third transition series to have atomic sizes very similar to those of the second transition series, despite being in different periods. For all lanthanoids, the most common and stable oxidation state is +3. This is because the +3 state leads to a stable F orbital configuration. However, certain lanthanoids can exhibit other oxidation states. For example, cerium can show the +4 state. Europium can exist in the +2 state, and terbium can also display the +4 state. Oxidation states other than +3 are observed when the element gains extra stability from an empty, half-filled or fully filled F orbital arrangement. A notable example is cerium in the +4 state, which acts as a strong oxidizing agent because it readily gains an electron to revert to the more stable cerium in the +3 state. Lanthanoids are generally quite reactive, and this reactivity is especially noticeable when they are in finely divided form. In air, they tarnish quickly as they form protective oxide layers on their surface. They react readily with dilute acids to produce hydrogen gas. For example, 2 atoms of a lanthanoid metal react with 6 molecules of hydrochloric acid to produce 2 molecules of lanthanoid trichloride and 3 molecules of hydrogen gas. Spelled out, the reaction is 2Ln plus 6HCl produces 2LNCl 3 plus 3H2. Most lanthanoids exhibit the +3 oxidation state in which they form stable M3+ ions. Their salts are usually colorless or pale in appearance. This is because electronic transitions between F orbitals, called F to F transitions, are Laporte forbidden, making the colors less intense compared to transition metal compounds with D to D transitions. In this setup, a piece of lanthanoid metal is placed in a flask containing dilute hydrochloric acid. The lanthanoid reacts vigorously with the acid, producing bubbles of hydrogen gas that rise to the top and escape. The reaction taking place is 2Ln plus 6HCl produces 2LNCl 3 plus 3H2. The lanthanoid dissolves to form lanthanoid trichloride in solution, while the hydrogen gas is released as seen in the upward movement of bubbles. This experiment visually demonstrates the high reactivity of lanthanoids with acids and their tendency to form M3+ ions in solution. Speaking of color, let's explore what gives lanthanoid ions their subtle hues. Unlike D-block elements, which show strong color due to DD transitions, lanthanoids exhibit color through FF transitions. These are transitions between energy levels within the same 4f orbital, and because the f orbitals are so deeply buried inside the atom, the transitions are weak and result in soft, pastel-like colors. For instance, neodymium 3+ gives a lavender hue, while praseodymium 3+ gives green. Magnetic properties also follow suit. Many lanthanoid ions are paramagnetic, meaning they're attracted to magnetic fields due to unpaired electrons in their 4f orbitals. What's interesting is that because these orbitals are shielded by outer electrons, their magnetic behavior is not easily affected by the surrounding environment, making their properties predictable and stable. From magnetic resonance imaging to high-strength magnets, these traits have real-world importance. Despite their fascinating properties, lanthanoids are quite a challenge to isolate, and that's because their chemistry is so similar. Most of them form +3 ions of almost the same size, making their separation from each other tricky. Traditional chemical reactions don't help much here. That's where specialized techniques like ion exchange chromatography and solvent extraction come in. In ion exchange, lanthanoid ions are passed through a resin that selectively binds ions based on size and charge. This allows individual lanthanoids to be eluted separately over time. Their tendency to form complexes is generally weak due to their large size and low charge density, but when they do, they often show high coordination numbers, commonly 8 or 9, wrapping around with ligands like water or EDTA. These separation techniques are not just lab curiosities. They are essential in obtaining pure lanthanoids for electronics, nuclear applications, and more. The lanthanoids are a series of elements ranging from cerium to lutetium, and they are characterized by the gradual filling of the 4f orbitals. Across the series, they exhibit several key trends, including the lanthanoid contraction, a predominance of the +3 oxidation state, and the presence of weak but distinctive color and magnetic properties. Chemically, lanthanoids are reactive metals, mostly forming trivalent ionic compounds. Their electronic transitions occur within the f orbitals, known as F2F transitions, which influence their optical and magnetic behavior. One of the challenges with lanthanoids is their separation. Because their chemical properties are so similar, purifying them requires specialized and often complex techniques. In real life, lanthanoids are indispensable. They are used in high-performance alloys, in the production of lasers, in phosphors for lighting and displays, and as catalysts in various industrial processes, making them vital to modern technology and materials science.